All right, good afternoon, everybody. My name is Krister Shalm, and my co-instructor here is Mike Mazurek. And we're both from NIST, the National Institute of Standards and Technology, and Mike's also at the University of Colorado here in Boulder. And we have the, I guess, honor or dubious distinction of being the last course of this winter school. And what we're going to be doing today is talking a little bit about quantum networking with path-entangled single-photon states. And so a lot of the course today is just really going to be explaining what that title means. And want to mention that for this course, I'm not going to read this description, but in terms of like what's going to be required, it is helpful if you have some undergraduate quantum mechanics experience or a solid engineering background. And we're going to be doing some very light algebra, nothing too complicated with linear algebra, just some very light algebra. And really, if you can count, basically to 2 or 3 and do some simple algebraic substitutions, that's about as much math as you will need for this particular course. And what we really want to do is for this course, we're going to be breaking it up into 2 parts. So overall, we're going to be talking about the very first quantum repeater or networking scheme that was scalable. And that is the scheme proposed by Dwan, Lukin, Serac, and Zoller in the early 2000s. And so this is the original networking scheme. This is something that Mike and I both work on. We're both experimentalists. We deal with photons and we try to build quantum networks. And so we're going to talk about this path-entangled method. And the first half of this course is going to be going through some of the basics of optics, kind of setting things up. We're not going to assume that everybody's taken all of the previous courses and really trying to get everybody on the same page. So if you've been taking some of the previous courses, this will be some review for you, reinforcement learning. And then the second half of this tutorial, we're really going to get into the nitty-gritty of DLCZ and entanglement swapping. So throughout the course, just like the other tutorials that have been held, we're going to be holding poll questions. And so just to get us started and to practice, we're going to ask our very first poll question to folks. And that is this week for this school, how many courses have you taken? So just go ahead and answer. Numbers are coming in. We can see them live. And it looks like we'll just leave this open for another maybe 10 seconds or so. But we have quite a few folks who have been here for pretty much the entire time. So yeah, it looks like some of you have taken all of them and most of you have taken several of them. So that's great. And for the folks who are, this is your very first course, well, welcome to the summer school. Or the winter school. Okay, so we're just going to get started with what I think is the biggest problem in optical networking. And I'm not just talking quantum networking, I'm talking classical networking too. So what I've shown below here is a single mode fiber, and that's a piece of glass that can carry optical signals. And this material, the glass I make is ultra pure, so there's very little loss inside of one of these fibers. They operate with total internal reflection, and you only get about 0.15 dB of loss per kilometer. That really means you get about over a kilometer of this glass and put in 1 watt of light, you're going to get about 96.5% of it transmitted through. Now, the problem is fiber and any kind of transmission line like this, those losses accumulate exponentially. So if you go through 10 kilometers of fiber, then your transmission through it is like 0.965 to the power of 10. So what would happen if you just wanted to send a signal through a fiber that's about, say, 4,000 kilometers to Los Angeles to New York City? Well, that would accumulate about 600 decibels of attenuation, meaning that your signal is attenuated by a factor of about 10 to the power of minus 60. And that's a huge number. In fact, that's an astronomical number. And I do mean that literally. Like if you just looked at, for example, the sun puts out roughly, according to NASA, its luminance is about 3 times 10 to the 26 watts. Now, 1 watt of visible light contains on the order of 10 to the 19 photons per second. And that's what a watt is equivalent to. And so the sun itself is putting out about 3 times 10 to the 45 photons per second. And if you think that there's about 100 billion stars in the galaxy and they're all about as bright as the sun, that's about 10 to the 56 photons per second that all the stars in the galaxy are putting out right now. And so this is obviously not possible, but if you could take all of those photons that they produce in the galaxy and shove them into one end of the fiber in Los Angeles, on average, you need to wait several hours just to get one photon through. So that's what the average time for emission. So clearly that's not going to work for optical networking. And so the classical solution is to use amplification. And so you've got some signal right here that you're going to encode optically, and it's got some power, and then you send it through roughly 100 kilometers of fiber. That's the typical number for a repeater distance, or sorry, an amplifier distance. It gets to, the signal decays down exponentially, and then you boost it up with these amplifiers until you get to your receiver and you can decode it. And that allows you to overcome this kind of exponential loss. The problem with quantum systems, though, is you can't make copies of an entangled state. You can't use this amplification because of the no cloning theorem. So instead, what we need to do is, instead of amplifiers, we need to replace them with a different mechanism, and that is using entanglement to overcome the loss through quantum repeaters. And so in the second half, Mike's going to tell you about this quantum repeater architecture that's based on path entanglement. And I'm going to, for the first part of the talk, go through and describe how we can, what is path entanglement, and and some of the basic properties of some of the elements that we're going to be using for the rest of the talk. So I'm going to go and, for those of you who started and took the very first course of this quantum networking school, the very first course was taught by Saikat Gua and Mike Raymer, and they spent a lot of time going through deriving the states of light and the simple harmonic oscillator model of light. So I'm not going to spend a huge amount of time going through it, but we are going to review it because we're going to be using a lot of those results. So here on the left is a simple harmonic oscillator. It's just a mass attached to a spring, and that's oscillating up and down. And what you can see is it's going up and down with some from some plus y to some minus y position. And what I've plotted here is this parabola. This represents the potential energy of the of the system. So our second poll question is, right now, this is oscillating between 2 points, y and minus y. What happens if I were to take this spring and instead pull it down twice as far and release it? So now I put way more energy into the system, and it's going to oscillate up and down. What happens to the period? Does the period stay the same? Does it halve? Does it double? Or, I don't know. That's a valid answer too. So we're going to keep that open for just a second. Okay, so over half of the folks have answered. So the answer is it stays the same. That's one of the properties of a simple harmonic oscillator, is it takes to get to its endpoints, the time to the period of oscillation stays the same no matter how much energy you put into it. It's dictated by the spring constant and the mass. Okay, so let me just move on here from the poll. When you take light and you take Maxwell's equations and you solve them, what you find is the electric field also behaves in these, it operates in these modes that can be described by a simple harmonic oscillator. And when you go and you quantize that state of light, that electric field, Maxwell's equations, you go through that quantization process, what you find is that it is no longer continuous. You're no longer, can you oscillate, at any continuous or along this kind of continuum, but rather the energy levels are discrete. So, you can either oscillate in this first state, which we call the vacuum, or you put one quanta of energy in and you can oscillate now between these two endpoints and so on. So you end up with a discrete energy level structure. And there are operators that we can define that allow us to go through these transitions. So just a note about notation here. This is what we call a ket, and it's 0, meaning this is our ground state of the system, or what we'll be calling for photons, the vacuum. And if I want to go from one state to another, I can use a creation operator that adds energy to the system, adds one quanta of energy. And when you're in the first excited state, that's a single photon. That's what we'll be using that notation. So we go from the 0 state to the 1 state. If you start instead from the 1 state and you go to the 2 state, well, now you added another quanta of energy and the amplitude changes to √2. If you start from state 2, you can go to state 3, and so on and so forth. And so if you're in the nth excited state, you can use a creation operator will add energy to the system and take you up to the next discrete energy level. And these energy levels are all equally spaced. So this is because this particular mode of light is oscillating with a fixed frequency. The frequency stays the same as you're adding more and more energy to it. Now, at a very useful formula that we'll be using later on is that if I start from the ground state, or what we call the vacuum for photons, and I add n photons, or I want to kick it up with n excitations, then the amplitude is going to scale as the square root of n factorial. All right, so this should be familiar if you've taken some of the other classes. Similarly, we can have annihilation operators. So if we start from 3 quanta of energy in our system, then the annihilation operator takes us down to 2 state. Start from 2, we go down to 1, 1, we go down to 0. If we're in 0, we stay in 0. So in general, you take away 1 unit of energy from your system with the annihilation operators. And the annihilation operators, they do not commute. So that's another useful fact. Okay. Now, we have photons, and we're talking about these oscillating in a single mode with a single frequency, but really that doesn't exist in nature. We never have things that are just one pure tone or frequency. They're always going to be in some superposition of different frequencies. And instead, it's a little bit more accurate to write that down as having some kind of envelope function that's a superposition of different frequency modes. And what that function is, that envelope, is going to depend on the process of creating the photons. So, for example, if you have atomic systems or atoms, when they emit photons, they often emit them in this kind of Lorentzian type line shape. Other systems of generating photons might be Gaussian, and this could, in principle, be really almost anything. And also, photons, as they travel, they have spatial modes. So, for example, photons emitted in free space can have a transverse spatial mode. So that's the kind of x and y coordinates. So if the photon's traveling into the screen, x and y are sort of all around it in a transverse direction. And one common basis for representing these is these Hermite-Gauss modes. If you have a single mode fiber or an optical fiber, which we often use for quantum networking, then you can use total internal refraction, and there are boundary conditions here that confine the light to a particular mode. So we have this kind of spatial function that we now have to integrate over for our photon. But for the purposes of the rest of this course, what we're going to do is assume that all the photons we talk about are going to be indistinguishable. So they have the same spatial function and the same temporal functions describing them, and they arrive at the same time, and so on and so forth. And if we do that, then we can make this really nice simplification where anytime, instead of writing this whole wave function out, what we can do is just replace it with just an A dagger acting on 0, and that creates a photon in the excitation mode of A. So that's going to be a nice simplification, and it's going to make the math quite a bit easier. All right. So what we're going to do now is talk about some common optical elements. So elements that we use all the time in the lab and are really essential for the kind of quantum networking tasks that we're going to be using. So first one is a beam splitter. And what happens is there are 2 input modes, A and B. They interact on this, interface. And if you're in mode A, then a photon can either be transmitted to mode D or reflected to mode C. If you come into B, it can either be transmitted to C or reflected to mode D. Now, quantum mechanics is unitary, and this element conserves energy. Energy is conserved. So it has to be unitary as well. And that means that the relationship between reflected and transmitted components is, there's going to be some restrictions on that. So here I've labeled these in terms of A, B, C, and D. For the rest of my section of the talk, it's going to be convenient usually to instead talk about the, what happens if you have a creation operator. How does that get transformed as it enters, and then talk about the output modes C and D and the creation operators that are acted on them. So here are the relationships. A has some probability getting reflected to C and transmitted to D, and B can get transmitted to C, and you get this minus sign reflection to D. And when you actually go through the conditions of unitary, you find out that that's the reason you have to have this negative here. The actual form of what reflection and transmitted are going to depend on the physical implementation of the beam splitter. And so there's lots of ways to make these beam splitters, and there's lots of different valid combinations. For simplicity today, we're going to use a parameterization where t is equal to cos theta and r is equal to sine theta, and that satisfies these conditions here. And the most common beam splitter we'll be talking about today is the 50-50 beam splitter, where you have equal probability of coming out C or D. And in that case, these are the transformations that we'll be using. For those of you who have done any kind of quantum computing or quantum protocols, this is also what we refer to as a Hadamard gate. Okay, so we're going to start with kind of a gentle ramp up. What happens if I send a single photon into this beam splitter? So that can get transferred to, again, C or D. Well, single photon acting on input mode A, we're going to say that's just a dagger acting on the vacuum state of 0. And we've got this tensor product with the other input mode here. I didn't draw it, but there's an input mode here, which is the vacuum in B. Now, we're going to do that. We're going to use the substitution that we talked about here in the previous slide and substitute in those relationships for A dagger. Well, A dagger just goes to 1 over root 2 C dagger plus D dagger. And now, because we've gone through the beam splitter, we're now acting on the modes on the other side, which are C and D. And so I can write this out as 1 over root 2, 1 photon, superposition of 1 photon in C and none in mode D, or I can have no photon in mode C and 1 photon in mode D. So it's going to be a little bit cumbersome to include these tensor products because these are technically vector spaces. So what we're going to do is just drop them. So we're not going to really use them unless we really need to call something out. Just know that they're there and they exist. And another thing that we can do to simplify our lives a little bit is at times it'll be convenient to just drop the 0 components. If there's nothing there, just drop it. And so we can rewrite this line as just 1 over root 2, 1c plus 1d. Okay. We're also going to just say, what is the probability of, say, the photon coming out port C? And to do that, what we do is we've got some state here of our superposition of a photon being in C and D after you go through the beam splitter. And we're going to look at the overlap to calculate that probability. We asked what's the probability of the photon end up in mode C. So we just look at what's the overlap with a single photon in mode C with our state. And so we take the overlap of these two things. And what we find is that when we're doing this computation, you get 1c, the overlap of a photon in mode C with a photon in mode D. That's just 0 because there is no overlap. This is 1c, 1c is just 1. That's probability 1. And then you're left with, you take the basically complex, the absolute value and square it of the amplitude that's remaining, and we get a value of 1/2. So that's a fairly straightforward thing to do. And we're going to be using this trick a lot, where essentially you can just look at the coefficient that's out in front of a particular mode, and then basically you can take that coefficient and square it. So we're not going to be doing this for all of the things. You can actually just usually look and see directly what the answer is going to be. Okay, so another common element that we use quite often is a phase shifter. And so what happens is in one of the modes, you can apply a phase shift. That's this e to the I phi term that gets added. Physically, all that means is we're going to delay one arm relative to the other. Well, that's a pretty straightforward thing to do. And you can see here, I've shown like here's the oscillation frequency. You hit the beam splitter and it goes into these two different parts. And the wavelength of the light is given by some lambda. And then this phase shift is some small relative offset between the oscillations of these two different paths. And that's like what we call the phase shift phi. Now, to give you a sense of scale, for optical light, say green light, that's one of the most common frequencies or colors from the sun. That wavelength oscillates with a frequency, with a wavelength, it's got a wavelength of about 500 nanometers. So very, very, very small. And phi is going to be, something that's smaller, just differences in those paths that are smaller than 500 nanometers. So we can also talk about the next element, which is a Mach-Zehnder interferometer. This is a single-photon interference. And all we're going to do is the previous slide, we got to this point in green. So now we've figured out that we've got a state here that's superposition of being in mode C and D, and there's a relative phase that we've applied by adding a delay to mode C. And we're going to hit this beam splitter here. We're going to add a second beam splitter, and we're going to see what happens as we, what's the probability of the light coming out mode E and mode F. And so we've got some updated beam splitter transformations here that we're going to just simply substitute into this equation. And when we do that, I'm not going to spend too much time going through this math. It's here. You can review it later on with the slides. But what you'll see is that you just do the substitution, you collect terms, and what you find is the probability that you get a photon in E and none in 0 is just going to have this coefficient here, which is 1 plus e to the I phi over 2. And similarly, the probability that you come out, or the amplitude that you come out in mode F, is just 1 minus e to the I phi over 2. And so if we ask ourselves, what's the probability of exiting in mode E? Well, then we have to take, again, the magnitude of this and square it. And so we take the term that's in front of the E mode, and you get 1 plus e to the I phi over 2. And you can expand this out. And now when you get to this step, we're going to use the handy, something known as the Euler relations. And what's going to happen is by substituting this in here, we see that the probability that the photon exits mode E is just going to be given by this kind of cos function. So when phi is 0, meaning that there is no phase delay in this arm, so C and D are perfectly in phase with one another, then all of the light exits in port E and none of it exits in port F. If we instead shift the wave function so that they exactly destructively interfere, then you get destructive interference in port E, so you get a pi phase shift, and all the light will instead come out mode F. So something I want to mention is that this is an incredibly powerful device, and it was invented, or at least discovered, before quantum mechanics. It was Michelson in the late 1800s who came up with it. He was trying to develop a tool to make very precise measurements between two different paths, like the change in the path, and to measure whether or not there was ether. So, did light, as it traveled through space, travel through some kind of ether? It was thought that as the Earth spun through this ether, you could measure these kind of differences. And with this device, by monitoring how much power comes out of these two ports, it's going to be directly proportional to the difference in path length between modes C and D. And so you have really like one of the best rulers we've ever developed for making precise measurements are these kind of interferometers. Just to give you an idea, I think one of the most the big giant technological marvels of this of our age is LIGO. It's this interferometer designed to test and measure gravity waves. And what you've got here is in this white building is just a giant beam splitter equivalent. And then you've got these two arms and you can send light along these two paths. Instead of rejoining them off somewhere in the distance with a second beam splitter, they just fold this back on itself and use the same beam splitter to look at how much light to do the interference in that same beam splitter. But it's the same kind of idea. And the kind of precision they get is incredible. The difference in these two arms that they can measure is something like 1/10,000th the width of a proton. So these make really good sensing devices, and we'll maybe say something about that a little bit later. Okay, so we did an exercise where we built up some knowledge of what happens if you put one photon into a beam splitter. Well, what happens if we instead send two photons into the beam splitter, one into port A and one into port B? Reminder, here are the kind of modes, or the beam splitter transformations. This is the input state. Now, there are four possible things you could imagine happening. So one is both photons get transmitted, and therefore they end up in opposite ports. Both get reflected, they end up in opposite ports. One gets reflected and the other gets transmitted, so they both end up going out the same port. You think about this as like two coins, and you can flip them heads or tails. So heads is C and tails is D. Then you can either get heads, tails, tails, heads, 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 or tails, tails. So our next poll question is, and I'm going to give you a few minutes to work this out, right? So just like we did before, you're going to start with this state here, and you're going to do these beam splitter transformations. And I want you to compute the probability of this happening. So what's the probability that the two photons exit from opposite ports? So you get a photon in C and a photon in D. There's two ways that can happen. Both are transmitted, both are reflected. So just take a moment and try to do this math if you haven't done this before, and do this computation. Okay, so most folks have answered, and we are going to we'll give you some last minute answers coming in. All right, going once, going twice. All right, sold. Okay, so we got a range of answers. The winning answer with 43% was that this shouldn't happen at all. There's zero probability of the photons exiting either port. And the next common answer was a third of you thought that it was 50%. And then there was some answers for, I don't know, 25% and 75%. Okay, so the answer is, let me just get this all out of the way, is that it's actually zero. We're going to get some interference effects between these two photons that are going to have things cancel. I also, before I go through this derivation for how this works, I just want to say that there's been some questions coming in, or people have pointed out very helpfully, there's a few typos on some of the slides. If you see them, just let us know, and we'll correct those before we send out the final PDFs of these slides. That's why you shouldn't try to do your LaTeX typesetting at 3 in the morning. Okay. So for this derivation, what's going to happen is we start with this A dagger, B dagger, acting on modes, vacuum mode 0 and A and 0B. We go through the beam splitter, so now we end up acting on the vacuum states of C and D, and we apply the beam splitter transformations of C plus D and C minus D. This is just a simple multiplication. So you do, C dagger times C dagger minus C dagger, D dagger plus D dagger, C dagger minus D dagger, D dagger. Now we said that these are exitings. It's the same mode C and D for that we're mapping to. And so these two things here, C, D, and is equal to D dagger, C dagger. They actually commute with one another. And so when we substitute those in, things actually cancel. And so these two terms cancel with one another, and you're just left with C dagger squared minus D dagger squared. And if you remember from a while ago, we talked about how C dagger squared is equal to C dagger squared acting on the vacuum. And that's just going to give you a √2 over 2 amplitude. So that is where we get this √2 over 2 from. And so what you find is that you have a 1 over √2 amplitude of having both photons be in C, and a 1 over √2 amplitude of them coming out in mode D. And when you take the probability of that, that's just going to be 50% of the time you get both photons out in C, and 50% of the time they come out in D. Okay, what we're going to do is I'm going to ask this question again, but slightly different. What happens if the photons were instead distinguishable from one another? So maybe they don't hit the beam splitter at the same place. So so now we're going to have a total of, we have two input modes, and mode A gets mapped to mode C1 and D1, and mode B is going to get mapped to mode C2 and D2. So these are not the same modes. We've got 4 output modes that we're going to be looking at. And again, there are 4 things that can happen. Either both photons are transmitted, or both are reflected, or one is transmitted and the other is reflected. And so I'm going to ask that same poll question again, but now for this case where things are distinguishable. And so what's the probability of both photons coming out in opposite ports? So both being transmitted or both being reflected. Okay, going once, going twice, and we're going to close the poll. Oh, there we go. Okay, so the dominant answer is it's 50% now, and that is exactly correct. What we find is now, when we do the same type of thing, there's actually 4 modes instead of 2 on the output once we go through the beam splitters. And now C1 dagger, D2 dagger is not the same thing as D1 dagger, C2 dagger. They're just different modes. They're different quantities, so you don't get the cancellation anymore. And instead, things behave more like the coin flips. There's no interference. And so for a lot of these quantum effects that we're going to be dealing with or looking at or trying to take advantage, it's really important that your photons that are incoming are actually indistinguishable from one another. They need to be mapping to the same modes in order for you to get these interference effects. So I want to just mention one other thing here, and I didn't draw this out, but this is the basic tool. This is the way that I do like maybe 95% of the when I'm trying to solve a particular circuit or a gate or trying to figure out what's going to go on in my optical setup. This is the type of math that I use, is just these simple substitutions, and it is simple, but it can also get very complicated very quickly. And if you this kind of Hung-Mandel interference between these photons coming in, and photons are bosons, and that's why you get this kind of interference effect at these beam splitters. If instead I took, say, like, I don't know, 40 photons, and I put it through a network of a couple hundred beam splitters, and I said, the photons are going to be coming into different input modes, and then all the beam splitters are kind of linked together. And then I say, what's the probability of getting n photons out of one particular mode at the end? That setup, you can use the same type of math to go through and model. However, it's extremely challenging to compute. In fact, it's computationally infeasible for normal computers to do that. And it's called boson sampling. And you actually need to just run the experiment with these kind of optical devices. So yes, this is the basic elements, but as soon as you start chaining these together, it becomes extremely complicated very fast. Okay, so we're just going to move on and switch gears a little bit and talk about qubits. So you've heard a lot about qubits throughout this course. We won't belabor this too much, but you can essentially encode quantum information as a superposition of 2 different quantum states. And so this is a general representation where you have some state which we'll call 0 and some state which is 1. And there's going to be different amplitude probabilities between these two components. So this is a convenient way to parameterize a qubit. What you've heard a lot about over the past, if you've taken some of the previous courses and I've talked about some qubits, are using 2 different modes. So you have an excitation that's shared between 2 different modes to encode your quantum state. So it could be path, like either your photon is in this path or path C or D. It could be different spatial modes. So maybe my photon is either in the first Hermite Gauss mode, the 0, which is a Gaussian, or the 1, 0. And I can have these as my kind of basis states that I'm going to use to encode my qubit in. A very common one is polarization. So as light travels, it oscillates. And it can oscillate vertically, it can oscillate horizontally, it can oscillate diagonally, it can even oscillate in kind of a circular fashion. And so you can use the direction of oscillation as your kind of basis states to encode your quantum bit. What we're going to be doing is instead going back to our simple harmonic oscillator, and we're going to be using these energy states of 0, which is the vacuum, 1, 2, 3, 4 photons, this kind of number basis to encode our information. And in fact, if you just want to have a single excitation, then all you've got is a quantum superposition of being in the vacuum or being in the first excited state. And this is a way, this is kind of the operator representation where the vacuum component is just going to, when we try to break it up into this operator, it's just going to be the identity. Any kind of harmonic oscillator you can do this with. So for example, if you had an atom and you couple this qubit state of light into the atom, then what happens is when you interact with the atom itself, you go from the instead of the vacuum state, that's what we call the ground state of the atom. And then you either can excite it or not with these probabilities. And if you excite it, you end up in the excited state and you get this kind of ground excited encoding for your quantum bit. And we can also, in this type of encoding now, a single photon hitting a beam splitter generates entanglement. So we've got here, this is one of the Bell states. And now we can go back and look, we did the math for this earlier, and you can either have an excitation, so single photon in mode A and not in mode B, or in mode B and not in mode A, or and one, sorry, not in mode A and one in mode B. And so you can have this representation, this is a Bell state, and the state of the qubits of these two qubits of mode A and mode B will share a single excitation. They're entangled with one another. You can't write it as a product of what's happening in A times what's happening in B. So it's inseparable and therefore entangled. And by changing these beam splitters reflectivity and adding a phase shift, you can actually generate a more arbitrary encoding of that particular Bell state. Okay. Just to end off here, what we're going to do is we can also put atoms at the endpoints. And then what happens is when you interact with the atoms, then the vacuum again, where it goes to the ground state, and we can instead transfer this path entanglement between the photon being in these two modes to being in this kind of excited ground plus ground excited representation. And so now we've got entanglement between the two different atoms. All right. So we're going to take about a 5-minute break here, but I just want to say that for quantum networking tasks, I think that there are really 3 different things that you can do with a quantum network. And the first is quantum communications. So transmitting quantum states, secure communications, distributing entanglement. The second is if you can distribute entanglement, then you can entangle remote quantum processors together to create a larger quantum computer. And then the final thing that you can do is quantum sensing. So we talked about LIGO and interferometers. Well, now you can actually entangle different quantum sensors together to potentially improve the precision and beyond what is possible just with classical states of light. What we're going to be doing for the rest of this session is to be focusing on this first topic, quantum communications, and in particular, transmitting quantum states, secure quantum communications, and distributing entanglement. So we'll take about a 5-minute break here and reconvene at about 1:48 my time. I'm a mountain time. Okay. Okay, so we're going to come back and get started again. So there's been a number of questions that we've been trying to answer in the Q&A, and there's a couple of questions that I think would be helpful to address to everyone. So the first is, for a path entangled states, we're sending in a single qubit, a photon, that then becomes two entangled qubits. And that is almost what we're doing. What we're actually doing is sending in a single photon right here. So, you could think about it, if you want to call it a qubit. In this case, it's just the one. But what we're really doing is generating. I prefer to think about this as sending in a single photon, and then that photon ends up, what you're really entangling, the degrees of freedom are the path that the photon takes and the relative phase shift between those two paths. So it's a modal type of entanglement. Normally, in a lot of other encodings, what people are used to are, everybody gets their own qubit. And so I've got an atom, you've got an atom, or I've got a photon and someone else has a photon, and those are entangled. Some property in those photons are entangled with one another. But modes are first-class citizens, and they can also be entangled with one another as well. And you can take those and, again, as we showed, couple those to atoms. So now what you're sharing is an excitation amongst two atoms, and I can operate on my atom, which is that harmonic oscillator, or you can operate on yours. Now, the other question we got is, won't the excited atom decay to the ground state by emission after a while? Absolutely. But when they're first, this process first happens, you do have this state here. And if you can do your operations on a much faster time scale than that emission time, the average emission time, and then you can actually, proceed with your kind of entangling operations. Mike is going to talk more about this in the second half, though. So these are great questions. Okay. Continuing on, what we're going to do is start off by talking about transmitting quantum states. Now, this section right here, we're going to really talk about quantum teleportation. And this was also covered in, I believe, the first day, the second set of talks, also by Mike Raymer. And so we're going to revisit this, but in the framework of path entanglement. So we talked about how it's hard to transmit quantum states because of loss, say in fiber. Well, if instead, this is a picture of the Chinese satellite experiment, NIST, that happened a few years ago. You got a satellite and it's distributing entanglement between two stations. What you could do is use that entanglement to then, as a resource, teleport or transmit using the entanglement your state from, say, one station to the other. And so what this looks like without the satellites and all the other paraphernalia in the path-entangled version is the following. So we're going to use two beam splitters here. And what we're going to do is we're going to put it in some path-encoded qubit. So it's in a superposition of the zero, the vacuum, and the one photon excited state. And we're going to represent that as cos theta plus e to the I phi sine theta. Those are the different terms in front of the 0 and the 1. It's going to be easier to just write cos theta is equal to A, and e to the I phi sine theta is equal to B. And so that'll just simplify the math a bit. And what's going to happen is we generate, with a photon on this beam splitter here, path entanglement. And if we do things right, then with the correct operations, we should be able to have that input state, that qubit state, end up coming out mode F. So, and I've written this in terms of the operators here of how we expect things to transform. Okay, so what happens is we'll start in the bottom here. We take a single photon in, and now we create this path entanglement between modes B and modes F. So we write that state over here. That's our Bell state. And then the half the mode, the B mode here, that's half of this entangled state, is going to be interfered on this beam splitter with our input mode. So we're going to get kind of a Hungel-Mandel-like effect. So we've got two different modes here. And then we're going to have the outputs in C and D with detectors at either end. So we can do our beam splitter transformations. We start with our input state, our unknown qubit that we want to teleport. interacting with this path-entangled state in B and F. And so this is the, we can write this out. We've got three different modes in play, modes A, B, and F, or inputs. And something I'm going to do just to simplify things and be a little bit lazy, it's convenient for this, is I'm just going to say all of these vacuum states, I'm just going to call them as just this generic 0. So this is really representing this, and that's just, it's a common trick we often play. So we do the beam splitter substitutions like before, and you now had some experience with it. And what happens is if we go through and we go to collect our terms in terms of the coefficients A and B, what we find is, we've got this one term here that's a C plus D and one that's C minus D, exactly like the Hungel-Mandel. And if the photon in mode B is indistinguishable between the excitation of a photon in mode A, then you get perfect interference. And so that's the Hungel-Mandel interference here. That's that C dagger squared minus D dagger squared that happens. And so we end up with this kind of mess after we go through this beam splitter C and D. What we can do is collect terms in for the C daggers and the D daggers. So if there's one photon in mode C dagger, then this is the state we get out. If there's one photon in mode D dagger, we collect these terms and we get this state. If there's two photons in mode C, you get the C dagger squared, which has this B2 over root 2. Similar thing if you have two photons in mode D. If there are no clicks here, so no photons end up in either of these modes, then you just get some kind of vacuum state A over root 2. So let's look at the case where we just get a click in mode C. And what we find is that, again, we've got this thing here. We collect the terms. We get C dagger over 2 of AI plus BF dagger acting on the vacuum. And lo and behold, that's just equal to one photon in mode C, tells me that this is that original state we were trying to teleport. So if I get one click over here, then with a probability of 25% or 1/2 squared, then in mode F, you've actually teleported the original input state. However, if I get a click on a single photon in mode D, then what happens is I don't actually get this state out. I get almost the state out. I get A0 minus B1 in the F mode. And so it's off by a pi phase shift. So what I can do is signal, I could send a classical signal saying, hey, we got a click in the D mode. Your state isn't quite what it should be. You need to add a pi phase shift, a phase shift to it. And then in the mode F, you can add this phase shift and correct and get the correct state out. So we call this operation feed forward, and it allows this kind of quantum teleportation to succeed a total of 50% of the time. Because if I get a click in C or a click in D, that will allow me to get this output state here. There are some other things that can happen. For example, neither of these detectors could click, or I could get 2 photons detected in C or 2 photons detected in D. In those cases, those are error modes. They happen a total of 50% of the time. And in that particular instance, the teleportation fails and you have to try again. So this, anytime you have this kind of beam splitter operation and you're detecting photons on the output ports, this is sometimes what we call a Bell state measurement. Mike's going to talk a little bit more about them later on as well in his section. And they can be used for these kind of swapping or these kind of teleportation operations where, you take an entangled state or some kind of input state, and then you can have it appear on a different output mode. So just wanted to briefly mention, and again, Mike will talk more about this, but I can replace my beam splitter in the detectors with instead 2 atoms. And I can take my input state here and couple it to an atom. And so I can convert it into an atomic ground excited qubit. And same thing with this B mode for part of the path entangled state. I can also encode it in this particular atom. And then you can do the equivalent of what we just did with the Bell state measurement, but you can do the atomic version of it. And with atoms, you can actually do this with 100% probability, meaning that every time you send in one of your input states to get teleported, it always can be outputted. Now, there's a few more corrections you need to do, depending on which of the outcomes you get, but it will always succeed. So Mike's going to talk a little bit more about the atomic Bell state measurements in the second session. So what I want to do is, with my remaining time, talk a little bit about secure quantum communications. And this is one of, I think, the applications of a quantum network, and probably will be one of the first strong applications of a quantum network. And really, when you're talking about security, not just quantum security, what you're really trying to do is safeguard information. Maybe it's like you've got a PIN code that locks some data on your hard drive and it encrypts it. Or maybe you're trying to communicate to people, two people are trying to communicate securely and send information back and forth without somebody in the middle trying to discover it. And that's cryptography. And you're trying to guard against always some kind of hacker or bad actor that is trying to break or discover your secrets or break your encryption. And one of the most, I say, fundamental aspects of security is randomness, because randomness, by my definition at least, is something that is unpredictable. And so if something's truly random and couldn't be predicted in advance, then a hacker can't discover or guess in advance the outcome of the randomness. And we use randomness to generate keys, to secure data, in lotteries, resource distribution. It's a very kind of fundamental thing. And one of the biggest problems with any kind of cryptographic system, quantum or classical, is you have to make assumptions about how your system works. And the big thing we're trying to guard against are side channels. So just to kind of illustrate a side channel, I'm going to play a video. I just discovered when I logged in, unfortunately, the audio is not going to play. So I'm going to try to narrate this video as we play it. So this is from TikTok. And there's a guy, he's living in a gated community. And he's asking the question, he's got this gate here, and he wants to know how secure this lock is in this gated community. You have to put in this code to get in, and only the residents know. I mean, maybe it's pretty secure, but can the gate lock be hacked? So he just wants to show us again how the gate process works, and you can open it up. You just have to enter the code. You go in. Seems pretty secure, right? Okay. So this particular system, that lock was probably a pretty good lock. And that gate is probably a decent gate. And that system is designed in a particular way to be secure. Unfortunately, it's got a pretty obvious side channel involved in it. Okay. So we're going to ask a poll question right now. And that is, I'm going to take a 50-50 beam splitter. I want to make a random number generator. So let's make a really good random number generator. We talked about how a beam splitter is probabilistic, and it should be a random process. So I can send a photon to a beam splitter, and if it comes out this port, I detect it in the up port. I call that a 1. If I detect it in the transmitted port, it's a 0. Okay, so we're going to make a beam splitter of this. Is this a good random number generator? Okay. So I'm going to end the poll now. We've got most folks have responded. And so I'd say the majority of you, 2/3, think that it is a good random number generator. And most of the rest think that it is not, or maybe it could be. Now, really, all three of these answers are correct. But what I would say is, for the purposes of today, having tried to build one of these random number generators, I'm going to actually say, I'm going to lean towards it being no, it's not secure, or maybe it's secure. It really does depend. And the reason is because, yes, I believe quantum mechanics is random, but there's a whole host of assumptions about what's going on here. So maybe I think this is a 50-50 beam splitter, but perhaps it's not actually 50-50. Or maybe wavelength of the light coming in, I think it's a particular color. Maybe it's a different color that behaves differently on this beam splitter, or perhaps these detectors are temperature sensitive. And so by changing the temperature, you can change whether you get a 1 out or a 0 out. And all of these are things that I have personally encountered when trying to build these as random number generators. Yeah, a photon and a beam splitter should be random, but there's all of these other things that you need to consider about your system and make a full characterization of your device in order to really understand how it behaves. So if you can do that, and you can characterize all the possible side channels that exist, the things that are outside you didn't account for. If you can try to account for as many of those as possible and design extra constraints around it and security measures, then actually, yeah, you can actually turn this into a very good random number generator, and you can buy these commercially. But you do have to really understand the physics of what's going on, because if there is a side channel you haven't accounted for, or some other parameter or degree of freedom, then a hacker could be using that to either predict ahead of time the outputs or even control it. And you might think it's random, but in reality, it's not. So side channels are a huge issue, and they come up even in quantum systems. So we're going to switch gears for a moment and generalize this a bit. Because when quantum mechanics first came out, one of the things that disturbed folks like Einstein and that led to the Bohr-Einstein debates is this kind of probabilistic nature of quantum theory. So, for example, a photon hitting a beam splitter, that behaves very differently than what you would expect in classical physics. In classical physics, if you know the position of momentum or the initial conditions of a system, then you could exactly predict what's going to happen. So instead of a photon and a beam splitter, if I flipped a coin, right, if I know, we think that's random, but if I know exactly how much energy I'm putting into the flip, I can predict exactly if it's going to land heads or tails. In fact, I've got a friend of mine who's a magician who, if he can flip coins and as the coin's in the air, you can call heads or tails, and he can always make it come up that way. So the thought was that maybe quantum theory, this probabilistic description of nature, maybe it's not complete. Maybe there's something that we're missing. There's a better theory that you could come along that you could amend. There's actual extra parameters, and they might be hidden from us, that if we knew what those parameters were for this photon coming into the beam splitter, we could tell with certainty whether it was going to get reflected or transmitted. We don't have access to them. So, okay, fine, it looks probabilistic, and we have to use statistical methods to try to describe things. But in principle, deep down, maybe nature really is deterministic. And so the question, the kind of point here is that these local hidden variables, these extra parameters that maybe we don't have access to, that are really telling you what's behaving, the side channels we just described that a hacker would use to take control, those are formally equivalent, or they're actually examples of a type of hidden variable theory. So they're both are parameters that, if known, remove the probabilistic nature of the system. So my question is, are local hidden variable theories compatible with nature? More specifically, are they compatible with quantum mechanics? And the answer is no, they're not. This is the marvelous theorem from John Bell. Now, I'm going to talk about John Bell's theorem. And again, you heard about this if you took the courses on the first day, the second session. Mike Raymer has a really nice description and a game that he plays. And he's even got a comic book that goes through and describes this. We're going to do a different version of the game. And really what we're going to show is that entangled correlations give different answers, or stronger correlations, than what you would expect from any kind of local hidden variable description of that system. So when I first heard about Bell's inequalities, I thought it was marvelous and also a little bit esoteric. And so playing this as a game does help, at least me, better understand how things behave. And again, our goal for going through this is knowing that if you have a system in entangled correlations, and you can rule out a hidden variable description of them, you're also ruling out any kind of side channels a hacker could use to take advantage and predict the outcomes. And so it gives us the strongest kind of security guarantees that we know of. And they're the best that I know of, at least. So the version that I like to play is we're going to reframe it a little bit. So don't take this too seriously, but this just kind of helps things be set up. We have two parties, Alice and Bob. Alice and Bob approach us and they claim that they're psychic, meaning they can read each other's minds instantaneously. And they're so convinced that they're psychic that they bet us $1 million that, you know, if we can come up with some kind of game or test that shows that they're not psychic and shows that they are frauds, they're going to pay us $1 million. But if they can prove to us, to our satisfaction, that they are psychic, well, we have to give them $1 million. So there's some incentive here. So what we're going to do is we're going to devise a game. Alice and Bob can discuss it, come up with a strategy, and then what we want to do is separate them out. So we're going to employ here our friend John Bell to be the moderator for this game. And so the first kind of test that I can think of that could possibly work is, okay, well, let's put them in a separate room because we want to keep them isolated from one another. And what I'm going to do is I'm going to put a piece of paper in each room. And on one side of the paper, I'm going to have a plus written. And the other side, I'm going to have a minus written. Now, we don't want to subtly influence these Alice and Bob characters in any way in how they answer. So what we're going to do is we're going to put a little light in each room. And John Bell's going to sit outside the room. He pushes a button. And then when the lights go off, we're going to make Alice and Bob answer. And Alice has to show us a plus or a minus. Bob has to show us a plus or minus. And we're going to say that the way they win is that their answers are correlated. So, for example, if the lights go off and they both show us a plus, they win that round of the game. If they both show a minus, they win. If they happen to show us opposite answers, then they lose. So we're going to play this game a bunch of times. And again, Alice and Bob can discuss beforehand, and agree with the rules of the game. And then we're going to separate them and play it. And so my question for the next poll is this a good test? Would you bet your $1 million on this game being able to tell whether or not they're psychic? Okay, so most folks have answered now. And we get about roughly a third of the people said that this is a good test, and 2/3 said that this is a bad test. So for those of you who answered yes, the main takeaway you should take away from this particular talk is that don't go to Las Vegas and gamble. This is actually a bad test. This is going to be a pretty easy test to cheat if Alice and Bob are nefarious. Okay, and the reason is because Alice and Bob, they're allowed to talk before we begin this test, and they could come up with a strategy to coordinate how they answer. So, and that strategy is equivalent to a local hidden variable. It's hidden from us, but it is something that coordinates how they answer. And so, for example, Alice and Bob, maybe they're really good at math and they know digits of pi. They've memorized lots and lots of digits of pi. Every time the light goes off, they go to the next digit of pi. So 3, it's odd. We're going to answer plus. The next one's odd. We're going to answer plus. They get an even number, they answer minus. And that's how they can coordinate their answers. The simplest strategy that they could come up with is just to always answer plus, no matter what. They will always win the game. They don't have to know, Alice doesn't have to know anything about what Bob's doing. Bob doesn't have to know what Alice is doing. They just answer plus and they always win. Okay. So we're going to modify this game slightly. What we're going to do is give Alice 2 pieces of paper. One's labeled A, the other's A prime. And Bob has 2 pieces of paper. We'll label his B and B prime. And so now each round, we're going to, same thing, John Bell over here, he's going to now pick, is it Alice's A light or A prime light that lights up, or is it Bob's B or B prime light that lights up? And if it's the A light for Alice, she has to answer with that piece of paper. If it's the A prime light, she has to answer with that piece of paper. And same thing for Bob. Okay, so we're going to change the rules of the game a little bit. And again, Alice and Bob can discuss beforehand before we put them in the rooms. They know how the game's going to be played. But here's how Alice and Bob win. right? Because there's 4 things that can happen now. So the first thing is that John Bell chooses the A and B papers. And so what we're going to demand is in those cases, if it's A and B, to win, they have to give a correlated answer. So the same thing as before, plus, plus, minus, minus. If A and the B prime lights go off, they have to both show correlated answers. If the Alice's A prime light goes off and Bob's B light goes off, again correlated. But if Alice's A prime light goes off and Bob's B prime light goes off, then to win, now they have to give opposite answers. So either plus minus or minus plus would be the winning combination there. So it's a little bit different than before. And so the question is, the next poll question, so Alice, she's got some strategy with Bob, and her inner light goes off, the A prime light goes off, and the answer is, how should she answer? Should she be correlated, anti-correlated, or you don't know? Okay, we're going to leave this open for another few seconds. So I'm going to go once, going twice. All right, we're going to end things here. Okay, so it looks like, we got a split between correlated. More people think we should be correlated. Some think we should be anti-correlated, and some people say we don't know. And the truth is, well, give me 1 second here. We don't know, because Alice needs to know which of Bob's lights went off, right? So if the B light went off for Bob, then she needs to give a correlated answer. But if the B prime light goes off, then she needs to give an anti-correlated answer. And I think right now, the reason maybe so many people gave correlated answers is I wrote this in a deceptive way by accident, showing kind of maybe pointing towards here. Really, Alice doesn't know which light Bob has, or which light has gone off for Bob. So she doesn't know. So there's a piece of information that's critical to her answering correctly that she doesn't have, because it's not under her control. It's happening dynamically and being picked by John Bell here. And that's what makes this a good test, because now there's something that Alice and Bob couldn't have prepared for in advance. So what happens if Alice and Bob are psychic and they really are able to read each other's minds? Well, then this isn't a problem for Alice, because she can just telepathically communicate with Bob, and Bob's like, yeah, my B light went off, and then they know how to answer. But so in that case, what we can say is, in each of these, for all the different combinations, if we give them a point for every time they get something wrong, and then take away a point for every time they get an answer incorrect, well, they get a total score of 4. They win every possible time. But what if they're not actually psychic? So what happens if they share a hidden variable now? And in fact, an optimal strategy is, no matter what the light happens, they just answer plus. That turns out to be an optimal strategy. It's not the only optimal strategy. And in that case, yeah, all the cases where they need to be correlated, just like before, they will win. But the cases where they need to be anti-correlated and give opposite answers, they will always lose. So if we did 4 trials, then what we would find is that the average score, the score that they're going to get, is 2. And we don't just want to do this experiment 4 times. We actually want to repeat it many times and take an average score. So every time they get an answer right, you get 1 point. Every time they lose a point, or get an answer wrong, they lose a point, and we take kind of the averages of this. And we can write down this inequality here. This is sometimes called the CHSH inequality. It stands for Clauser, Horn, Shimony, Holt. And you see that there's 4 terms. It's like, what's the average score when the AB light goes off, the AB prime light goes off, A prime B goes off, or A prime B prime. And this negative here is because they have to be anti-correlated. So there's an anti-correlation that comes up. With a hidden variable strategy, or we talked about maybe previously, if you had some kind of, which is formally equivalent to some kind of side channel, those strategies at most can have a score of 2. And that's the maximum limit for that. Well, what if Alice and Bob, instead of having a hidden variable strategy that they agreed on in advance, what happens if instead they share entanglement? And so now, instead of using their hidden variable strategy, like say these answer plus or use digits of pi to choose how they answer, what they're going to do is they're going to share entanglement. So we're going to send a photon to a beam splitter, and that's going to interact. And when it arrives at Alice and Bob, you're going to convert that to atomic entanglement between our two systems. And now, instead of John Bell, we're going to replace John Bell with a random number generator just to kind of randomize what settings Alice and Bob are, like what light goes off for Alice and Bob. So, and what's going to happen is Alice, when her light goes off, if it goes off with A, she's going to measure a particular spin projection of her atom. And at the end of that, if she finds that her atom's in the ground state, she answers plus. If it's in the excited state, she answers minus. Bob is going to instead make different spin projections on his atom, and he's going to do a similar thing. Depending if it's ground or excited, he's going to answer plus or minus. And so if they let the atoms pick and the correlations between the atoms derive how they answer, well, what we find is that instead we've now got this sort of expectation value, or their winning score on average for each of these different four conditions is 1 over root 2. And so the expectation value, the maximum you can do with quantum, is 2 root 2, which is bigger than 2. It's not 4, so quantum mechanics doesn't allow them to be perfectly psychic, but you could say in some sense that quantum mechanics is a little bit psychic in this case. So I kind of mentioned that we shouldn't take this too seriously, this game. And when I say psychic, you really can't use these correlations to send information faster than the speed of light or communicate. But you do have correlations that are stronger than those that are possible classically. And the fact that you can get 2 root 2, this is a fundamental result in quantum information. And those stronger correlations are what not only power a lot of the quantum protocols that we use and derive, but also it's the power for a lot of quantum computing, because these correlations allow you to solve certain types of computational problems faster than you could with a classical computer. So it's an incredibly powerful result. And I think this is like one of the simplest ways to describe where a true quantum advantage comes from. So let's forget about, before we kind of move on to, tying this back to the kind of quantum protocol with how you overcome side channels, I want to mention that there are still 3 ways that Alice and Bob in this game, could cheat, right? And the first one is, I put Alice and Bob in these different boxes here, and I put them in an isolated room. But like, what if I didn't take away their cell phone and they could just communicate? Or what if they've got some other hidden device that is allowing them to coordinate their answers? There was a famous cheating scandal in the last year in chess where somebody was using a hidden device to cheat. And so what you want to do is separate, ideally, the most fundamental thing is put Alice on the moon and put Bob on Mars, and then have them make their answers fast enough that they can't communicate with one another. So you could, space-like separate them. We don't have that budget, so we're going to do these experiments with photons and a much shorter time scale, because then you can make the operations fast and you don't have to go so far. A second thing that can happen is anytime Alice gets this light going off A prime, she can just refuse to answer. She can just say, I'm sorry, there was a device malfunction, I didn't see the light, and refuse to answer. So we should amend the game so that Alice and Bob have to answer at least some minimum number of times. And it turns out to really be able to rule out these hidden variable theories, you need to have them answer at least 2/3 of the time. So if you're sending entangled states to Alice and Bob, that means they need to be able to receive them at least 2/3 of the time so they don't lose the entanglement, so they're actually able to answer. And the final thing is Alice and Bob, how these lights go off needs to be random in order for you to, Alice shouldn't be able to look at her pattern of lights and be able to deduce what Bob is receiving. And so we often just use a random number generator to pick those settings. Okay. So these are sometimes referred to as the locality, freedom of choice, and no fair sampling assumptions. And if you can design an experiment that satisfies all of these conditions at once, that's what we call a loophole-free Bell test. And that is a very powerful system. And in fact, these aren't just theory, but there's been a number of these loophole-free Bell tests that have been done in the last 8 years. And here's the one that we did in Boulder in 2015. It was one of the first. We have a source that distributes entanglement to Alice and Bob. And Alice and Bob have to make rapid measurements on their qubits before any information can reach each other under these very strict conditions with very low loss. And so we've been able to demonstrate this experimentally, and we actually build systems based on this right now. And so just to wrap up, I just wanted to mention again that you could now use entanglement because entanglement rules out local hidden variable theories in these Bell tests under these strict conditions. You could now build systems, random number generators or other devices that use measurements on remote entangled systems to derive correlations that couldn't be explained by any kind of either local hidden variable theory, or if instead of a local hidden variable theory, you maybe trust quantum mechanics, but you don't trust your systems and how your entanglement's being generated and things like that. Well, you can guard against very smart hackers. And because you're also, by ruling out local hidden variable theories, you're also excluding all of those possible side channels. You don't need to take it to really take those into account. And so here pictured are, three of the Nobel laureates from 2022, Elena Spey, John Clauser, and Anton Zeilinger, who won the Nobel Prize for their pioneering work related to Bell's inequalities. And you really want to guard against the best possible hacker. So someone who has all the resources, maybe they have quantum resources, they have more money than you, they're smarter than you, and even with these kind of like super hackers, you can give them your source of entanglement. And as long as whatever they send you, you can violate this Bell inequality loophole free, you don't need to worry about any of the characterizations or side channels of the system. You can show and establish that you've got genuine correlations that you could use for randomness generation, for more advanced key distribution protocols, or there's a whole constellation of these new protocols that are called, say, device independent. And this is a very rapidly developing area, and it's something that a quantum network could be really good for, and is also something like doing these Bell tests because they're under such stringent conditions attached to them. They're very good ways to characterize the quality of your network. So we're going to take a break here for about 5 minutes. And we're going to switch over, and Mike's going to now talk about distributing entanglement. So how do you distribute entanglement in the face of loss? All right, so we'll see you folks back in about 5 minutes.
Okay, well, thanks. Welcome to the second half of this session. I'll just reintroduce myself. My name is Mike Mazurek. I know on the screen it says my name is Krister Shalm, but that's just because I'm using Krister's computer. I work at CU Boulder and NIST Boulder. And yeah, so in the second half of this talk, I'm going to talk about distributing entanglement. So thanks, Krister, for giving us a great introduction to what entanglement is, specifically path entanglement and some basic quantum optics operations, and also what you can use entanglement for. The two examples, that Krister mentioned were the quantum state teleportation and also device-independent secure quantum communication. So I'm going to talk about, so both of those protocols require you to start with entangled states that are distributed some distance, and I'm going to talk about how to achieve that. Okay, so in general, it's really hard to generate entanglement over really large distances, right? And we're here in this winter school in quantum networking, so I don't think I have to motivate spend too much time motivating the importance of a quantum network. But this is the basic reason. Entanglement can be useful, and it's hard to distribute it over large distances. Something that's not as hard to do, I'm not going to say easy, but much simpler experimentally is generating entanglement over smaller distances, or in a way that's considered local. So you might think that if you want to distribute entanglement over a long distance, what you can do is start by generating entanglement locally. And then just maybe you have these two particles, maybe they're photons, and then you just distribute them over a long distance. We know that that doesn't work very well. The main reason is because of transmission loss. For example, in optical fiber, but in any medium, when you're transmitting a quantum system or a photon, it's going to experience loss over distance, right? And loss affects your state exponentially with distance. So this is a plot of efficiency through some amount of fiber for various fiber lengths. And you can see from this plot that after only a few kilometers of very highly efficient fiber, I'm assuming a loss here of 0.15 dB per kilometer for those who are interested. So after about, I don't know, reading this plot, about 12 kilometers, the efficiency of that transmission channel drops below this 2/3 threshold. So if you were paying attention to the end of Krister's talk, you'll remember that in order to violate a Bell inequality, which is something that's necessary for enabling device-independent or secure quantum communication, you need to be able to detect the entanglement with an efficiency greater than 2/3. So if you're below this line, this application will not work. Okay, so the way to solve this problem is with a quantum network. And so I know what I'm about to show in the next few slides, I know this is not the first time anybody has seen this week. This has been covered in previous courses, but I feel like it's not bad to review. And I'm just going to do a very simple review here just to make sure that we're all on the same page and in an effort to keep this course self-contained. So bear with me if this is a little repetitive for some of you. So to generate entanglement over large distances, you can use a quantum network. And the one way to do that is you can start by generating one pair of entangled particles on a smaller distance scale, and then another pair and another pair and another pair. And you can generate this kind of chain of entangled pairs of particles in this kind of network configuration. And maybe you have two end nodes of the network and you have these nodes in the middle, which typically are called repeater nodes. And if you do the right operations in these repeater nodes, you can swap the entanglement between pairs and distribute it over longer distances. I'll go over this a little bit more detail later in this section of the talk. Anyways, you can do these for now nebulous operations and create entanglement between two ends of your network. Okay, and just I want to make a little note here on the terminology. So in Krister's part of the talk, he put up this picture of a classical network where there's a signal node and a receiver node, two end nodes of a network, and periodically every so often there's an amplification node, which amplifies a classical signal, or you might call that repeats this classical signal, and to overcome this loss limit. I really want to point out here that these quantum repeater nodes in a quantum network are not doing any amplification. They're doing a fundamentally different process. But I think the name repeater node is kind of informed by this idea of amplification in classical networks. Okay. So an ideal quantum network would have low errors and really high efficiency. So what I mean by that is that every time entanglement is distributed between the two end nodes, that entanglement can be detected very efficiently and also is very high quality, or so that you generate the entangled state you want with very small levels of error in that state. Ideally, the network will be able to distribute entanglement at very high rates, and then also that as you increase the distance of the network, the rates at which you create entanglement scales efficiently. So you can go to long distances. So in the first part of this, talk, I'm going to go over this famous DLCZ quantum networking scheme named after the 4 authors of this paper. And this is the a very famous architecture for quantum communication over a quantum network, which uses a mixture of excitations in atoms, or actually ensembles of atoms, and also photons. After I go over that, in the final section of this talk, I'm going to talk about a specific implementation of how you might implement DLCZ without using any matter-based systems and just using linear optics and single photon sources. Okay, so back to the picture, my cartoon of a quantum network. There's kind of two main components here. There's this local generation of entanglement here on the left, and then also these repeater nodes. So I'm going to explain how both of these sections of the network work, and I'll start with this local generation of entanglement here. Before I get into that, I want to talk about a very simplified version of a two-level system. So I'm really going to talk about an extremely simplified version of DLCZ in this talk. So I'm going to assume that you have some matter-based system, and maybe this is an ion and an ion trap. Maybe it's an atom, maybe it's a cloud of atoms, maybe it's a lattice defect that has different energy levels. It's just some matter-based system which has two energy levels, ground and excited. I'm also going to make the assumption that the lifetime of this excited state is extremely long. So, for the purposes of this talk, we'll just assume it will stay excited forever. Much longer, or on a much longer time scale than is needed to perform all the different operations in the quantum network. Okay, so if you have a system like this, then maybe if it starts in the ground state, you could excite your qubit from the ground state to the excited state by applying some strong laser pulse to excite it. And similarly, if the qubit is excited, you could imagine applying a different control pulse, which forces the qubit to decay. And when the qubit decays from the excited state to the ground state, it has to emit a photon of energy. And let's say this photon is emitted in this direction along this decay pathway. So if this happens, we could write the combined state of the qubit and the decay mode as the qubit being in the ground state, plus there being a single photon in the decay mode. This is the notation I'm going to be using. Okay, so you can imagine waiting some time, exciting this, letting the decay photon travel away and exciting this qubit again. Now we would write the combined state as of the qubit in the photon mode as excited and 0 photons in the decay pathway. Also, you could send in if the qubit starts off excited, you could send in a weaker control pulse, which doesn't force the qubit to decay deterministically, but maybe just with some probability, let's say 50%. If this happens, in this case, then what happens is you create an entangled state between the qubit and the photon decay mode, and you write that as this equal superposition of these two states that I showed on the previous slide. So the qubit's excited, no photon has decayed, or the qubit's in the ground state and 1 photon has decayed. Excuse me. Okay, so right, and so I'm going to draw this little entanglement setup symbol here to indicate that we've created this entangled state. In general, you could send whatever control pulse you want. You don't have to create a 50% probability of forcing the qubit to decay, but there could be some different probabilities. So maybe there's some probability that the photon does not decay, and some probability P1 that the qubit does decay. And then you would write the state here where each of these amplitudes is equal to the square root of those probabilities. A quick note on notation here. So in the first half of the talk, Krister was often using the parameterization for amplitudes of cos theta and sine theta when writing superpositions. This has the really nice property that cos squared theta plus sine squared theta is equal to 1. And this is required to conserve probability. I'm going to be using this different notation where I write amplitudes as square roots of probabilities. And it's always going to be implied that if you square all the amplitudes and add them all up, they all represent probabilities, and you sum all those probabilities together, then you get one. So the conservation of probability is just implied, just to keep the math look a little cleaner. Okay. So, so I talked about how you generate local entanglement between a qubit and a photon. And now I want to talk about how you could use this form of entanglement to entangle two matter-based qubits. So the way that you do this is you begin with two qubits, which I'm just going to call the left qubit and the right qubit. And each of these qubits have the specific decay pathways, which I'll label as modes A and B. And you can imagine sending the proper sequence of control pulses to both the left and the right state to prepare these qubit photon entangled states, one on the left and one on the right. And if this is the case, then you can write the total state of this system of the two qubits and the two photons as, so the system on the left is prepared in this 1/√2 ground 1 plus excited 0 state, so this entangled state, and the system on the right is prepared in the same state. So you write it this way, ground 1 plus excited 0 all over √2. And I'm just going to remove these control pulse and entanglement lines to clean up the figure here. And so after preparing those two entangled modes, what you can do is mix the modes of the two decay photons on a 50-50 beam splitter. I've also added these two phase elements here, phi L and phi R, and these are just supposed to represent the phases that any decay photons will experience as they travel from the qubit to the beam splitter. Okay, so, and yeah, so now because there's a beam splitter, we also have the two spatial modes C and D as well, and we put detectors in each of these modes. To keep things simple, I'm going to assume that these detectors can count photon number. So if one photon hits them, they'll return outcome 1. If two photons hit them, they'll return outcome 2. So we can tell the difference between 1 and 2 photons hitting a detector. And I'll talk a bit later about what happens if you relax that. Okay. So the first question is, if you start with the setup and you start with these two entangled states, what happens, and then you just wait and you look at these two detectors, what happens if you detect two photons among these two detectors? Well, one way to answer that is we can take this initial qubit state and we can expand it into these 4 terms, just using distributive multiplication, and look at all the 4 terms here. So the first term, there are two, both qubits are left in the ground state, or I should say both qubits emit a decay photon. So we have one photon in each of the A and B modes, which leaves both qubits in the ground state. In this term, you can have the qubit on the left emits a photon, but the qubit on the right does not. So it remains in the excited state. And now we only have one photon in the system. This other term is the same thing, but now the qubit on the right has emitted a photon. And then finally, we could say that both qubits just remain in the excited state and no photons are emitted. So the question is, if we detect two photons, what does that say about the state of the left and right qubits? And this, you can answer this by looking at this expanded form of the state of the whole system. So the only way to detect two photons is if each of these qubits emits a photon and they each go towards this beam splitter and they're both detected. And there's only one term in the global state of the system that has two decay photons in it, and it's this first term, which I've highlighted. And you could just see from looking at this that if we detect one photon in each, that leaves the left and right qubits in the ground state. Okay, so now it's time for a poll question. It's very similar to the last one. Let's assume that if there's any photons that are decayed from the atoms, let's assume they're detected with 100% efficiency. what is the state of the atoms if 0 photons are detected? Okay, I'll maybe give 5 more seconds for people to get their answers in. Gives a little more than 5 seconds of going once, going twice, and pull. Okay, so it seems like, so the answer, okay, here. So yeah, the answer is D, and that is what most people responded with. And the way that you can see that is the same way. The only way to not detect 2 photons is if both atoms stay in the excited state. And there's only one term of this global state of the equation that represents that. So if both qubits are excited, then there are 0 photons in the system. So the answer is D. Okay. The most interesting question. So I just talked about 2 possible outcomes you could get. You could detect 2 photons or 0 photons. Both of those cases, that does not lead to any entanglement between these 2 qubits. Neither of these 2 states are entangled. So the most interesting question is, if we just detect 1 photon among these 2 detectors, what state are the qubits left in? And just want to point out that what I've drawn here, this is the photonic Bell state measurement that Krister already showed us when talking about quantum state teleportation. The only difference here is that I've added these 2 phases that the photons can acquire as they're transmitted towards the Bell state measurement, and I'm including them in that Bell state measurement. But it's the same as we saw earlier already. Okay, so how to figure out what state are the qubits left in if we only detect 1 photon? I'm going to go through the math so we can figure this out. So I'm just going to redraw the setup a little bit smaller, move it out of the way here. And as a reminder, I put up the beam splitter transformations that the creation operators see as they propagate through this system, and also the transformation if for a phase shift. Okay, so the initial state of the system, it's this entangled state on the left and this entangled state on the right. And we already talked about how the only way to detect 1 photon is if 1 qubit emits a photon and the other one does not. And so there's only 2 terms where that's the case. So it's ground 1 excited 0 plus excited 0 ground 1. So what I'm going to do is cheat, and instead of keeping all 4 terms of this initial state in, I'm just going to get rid of the ones with 0 photons and 2 photons in them, and we're just going to keep these terms with 1 photon. That'll just make things a little bit cleaner on the slide. So the next step, I'm going to rearrange just the ordering of these kets here. So if we look at the first ket, the ordering is the mode of the left qubit, the A photon, the right qubit, and the B photon. I'm going to rearrange it to put both photons on the left. So it's now the A photon, B photon, left qubit, right qubit. And I'm doing that for this term on the right as well. And then I'm replacing the single photon ket, 1 photon in mode A, with the creation operator A dagger acting on the vacuum. And same thing for this term on the right, 1 photon in mode B, I'm replacing it with B dagger operating on the vacuum in mode B. Okay, so the next step now is to propagate the A and B modes through the phase shifters. So we just apply a phase of e to the I phi L and e to the I phi right to the A dagger and B dagger operators. And finally, now we propagate the A and B modes through the beam splitter. So A turns into C plus D over root 2, and excuse me, and B gets transformed to C minus D over root 2. Now, if we just take the state and rearrange the terms, group the terms in terms of C dagger and D dagger. So in other words, 1 photon in mode C, or the 1 photon ends up in mode D, then this is what it looks like. And you can see that we get these detection outcomes. So 1 photon in mode C multiplied by an entangled state on the 2 qubits. Okay, so this is the final result. I'm going to just take this equation and move it up to the top of this next slide. This is the same equation that there was. And now it's time for the next poll question. So if we run this experiment and the detection outcome that we get is that we detect a single photon in mode C, what state are the left and right qubits left in? All right, it's more people have answered now. So I'm going to end the poll. And the most popular answer was C, and that is the correct answer in this case. So if we take the initial state of the system and propagate it through, which we did on the previous slide, and we found out that this was in blue, this was the final state of the terms with only one photon in them. If you detect this first term has one photon in mode C and 0 photons in mode D, so that leads to this outcome, one photon here, no photons there. And so if you measure that outcome, that means you get this entangled state, which is answer C. Conversely, if you were to detect just one photon on the D mode and 0 photons on the C mode, then that would correspond to this outcome, one D photon and 0 C photons, and we'd be left with this other state, which looks almost the same as the state if we detect the photon in detector C, except there's this one important difference, which is this plus sign becomes a minus sign. So there's that very important phase difference. And okay, so this leaves the two qubits in an entangled state. Okay, so Krister just mentioned to me there are a couple of questions about how much time do we have to measure the photons after creating these entangled states. And something I guess I didn't do a great job of explaining, so I'll just go back and reiterate this, is I'm assuming that these control pulses are they're performed at the same time, and specifically so that when the two photons, if a photon's emitted, the time if a photon from the left is emitted, it hits this beam splitter at the same time that any photons from the right would be emitted. That's required to get good interference and for this entanglement creation to work. And then also, for simplicity, I'm assuming that the excited state lifetimes of these two qubits are very, very long. We could say infinitely long, so that the atoms will never decay unless we tell them to with this type of control pulse. Hopefully that clears a couple things up. Okay, so this process, it's commonly called entanglement swapping, and I'll use that term later throughout the rest of this talk. And the reason it's called entanglement swapping is because you start with a qubit photon entangled state on the left and a qubit photon entangled state on the right. Then you do some measurement on the two photons, and if it succeeds, then you end up swapping the entanglement from each of these pairs just to you swap the entanglement from the qubit photon entanglement to qubit entanglement. And so just a quick summary of all the different outcomes that can happen in this scheme is, so we said there's two failure outcomes. So if you detect two photons, both qubits end up in the ground state and you don't get entanglement. If you detect no photons, that's also a failure. Both photons or both qubits are in the excited state and there's still no entanglement. And in practice, if this happened, you were to run this experiment and you receive one of these outcomes and you just know that the entanglement was not successfully created, and then you would just try again. Conversely, you might get a successful outcome. So if we detect a photon, just one photon on the left side, you end up with this entangled state between the two qubits. Or if you detect one photon on the other side, then you end up with this different entangled state between the two qubits. And just like in teleportation, where we needed to use feed forward from the measurement outcome of the Bell state measurement to the to kind of correct any errors in that teleported state, we have to do the same thing with entanglement swapping as well. So for example, maybe the state that we want to generate looks like this. And so if we get this outcome, a photon on the left, then great, we've generated that state. That's what we want. But if instead we get the outcome where we've detect a photon on the right side, then we don't get quite the right state, but you can send a feed forward signal from the Bell state measurement to just one of the qubits and tell it to apply the right phase shift to turn this negative sign into a positive sign. And that's how you get a 50% success of creating this specific entangled state. Okay, so one important thing that I want to mention without going into any detail is this idea of phase stabilization. So the heralded, the heralded state of these two qubits, this entangled state, it has these two phase terms in it in the amplitudes. This e to the I phi L and e to the I phi R. And so what that means is that if the distance from a qubit to this beam splitter changes by some significant fraction of a wavelength of the photons, then that will change this phase by a significant value. So these paths need to be stabilized to within some very small fraction of a wavelength in order to make sure that we're generating the entangled states that you want, or so you could know with really high accuracy what entangled state was generated here. This is a really hard thing to do in general, especially if these photons are traveling over lengths of fiber, maybe kilometers of fiber. It's really hard to get that stabilization. And I would say that currently for this specific scheme that I've shown, this level of phase stabilization is an unsolved challenge. But on the other hand, this phase sensitivity could be a feature. So just like we use local interferometers to measure phase, this type of network can non-locally distribute a phase, which in principle could be used for very sensitive phase measurements over much larger distances than interferometers, even such as LIGO, which is already a huge interferometer. So if this phase can be tracked and controlled, then this opens up some possibilities for non-local quantum sensing, which are really exciting. But that's all I'm going to say about that right now. I won't go into more detail. Okay, so back to this cartoon, my cartoon of a quantum network. We just talked about how to do this kind of short scale entanglement distribution by using this qubit photon entanglement and then performing a photonic Bell state measurement on the two photons. So I'm going to draw these measurements in my cartoon of the network. And if you want to build up a chain of entangled pairs of qubits, what you can do is just try independently to generate entanglement on all of these pairs simultaneously. And say, for example, these three fail and this one succeeds. Well, so this one has succeeded, and that's great. And because we're assuming that we're in a limit where the lifetimes of these qubits are very long, then they act as really good quantum memories. They can store that excitation for a long time. So a time that's long on the scale of how long it takes to do all the quantum networking operations. So if this happens, and what we would do, these three failed, so we have to try them again on the next trial. This one we don't touch again. So maybe on the next trial, we try these two, they both fail. This one succeeded. And then we can keep this. Now we have two stored up. And then you just keep trying this over and over again until you've built up entanglement across all pairs of the network. So the next step here is to do operations in these repeater nodes. So I'm going to talk now about what that looks like. Okay, so here's a simpler picture with two pairs, just a 3-node network, I guess, with two, where I'll assume you start with two pairs of entangled qubits, and two of them are in a single repeater mode. And it's really simple. The operation that you have to do here is just another Bell state measurement. As Krister mentioned earlier in the talk, if your entanglement is between two atoms that are close together, or just any matter-based system, really, then in principle, it's possible to do a Bell state measurement that has 4 successful outcomes instead of just the 2 successful outcomes in the photonic Bell state measurement. And so, for example, if you get outcome 1, it maybe heralds this excitation of ground excited plus excited ground. Outcome 2, okay, so you did the Bell state measurement, and if it succeeds, then you destroy the quantum state of these 2 particles, and you leave particles 1 and 4 in an entangled state. So depending on the outcome, that depends on what state these 2 particles end up with. So it can be ground excited plus or minus excited ground, or ground ground plus or minus excited excited. And again, with the proper feed forward to each of these qubits, it's possible to do a correction so that, for example, you could correct all 3 of these outcomes. So no matter, you could correct all 3 of these states to look like this one, just with local operations. Okay, so that's the very simplified, very basic introduction to the DLCZ scheme. I've made a lot of idealizations. One big one is that the excitation lifetime of these qubits is really long, and I'm going to keep making that assumption for the rest of the talk. Another really big assumption I made is that the efficiency of all of these processes was 100%, and specifically that the transmission efficiency of the photons from qubit to beam splitter was 100%. And that's not a great assumption to make. If we had a 100% efficient transmission channel, then we would just generate pairs of, entangled pairs of particles locally, and then just distribute them among that channel. So it's actually really important to consider the effect of loss on this type of network. And that's what I'm going to do next. But before I do that, we're going to take another 5-minute break. So we'll come back at 3:13 my time. Right. Hi, I'm back. It's been 5 minutes. I just want to, can somebody confirm that my phones are, that my mic's still working?
Yes, everything looks good.
Okay, great. Thank you. And I just noticed that my video was off for my portion of the talk, so I apologize for that. I was doing a lot of hand waving, and I guess nobody could see it. Anyways, I'll keep it on for now on. Okay. All right, so over the break, I looked at a couple of questions in the chat, and one of them was asking about how the scheme is scalable if these Bell state measurements are not 100% efficient. I'm going to go into that in a lot more detail later on in the talk. But what I just want to say for now is that the way I presented it with all these idealizations so far is that each of these matter-based Bell state measurements is 100% efficient. So after generating all of these pairs, which we can do efficiently because we have long memories here, so we can just try each of these entanglement generation processes independently from each other and just wait till they've all succeeded. Then this final step, in this idealization where all of these repeaters have 100% efficiency or success probability, we can just run them all at once and the whole scheme will succeed. And I'll talk about what happens with worse probability later. Okay, but before I get into that, what if we just reanalyze this initial scheme, this initial short distance entanglement generation if there's imperfect efficiency in the photonic modes. So the way to model that, to answer that question, we have to talk about how to model imperfect efficiency. And it turns out in quantum optics, it's really easy to model loss. You just add a beam splitter into your system. So for example, say you have some transmission channel, maybe this is some length of fiber, and the total probability of your photon getting through the fiber is eta. So if the transmission channel has an efficiency eta, the way that we model that is just with some perfect efficiency transmission channel with a beam splitter put in. And this is an unbalanced beam splitter, and it has a transmission probability of the efficiency eta, and it has some reflection probability of 1 minus eta. So you just say that, light will remain in the mode that we care about with efficiency eta, or it'll be lost with efficiency 1 minus eta. Modeling in inefficient detectors is also very straightforward. Again, we'd use the same trick of just sticking a beam splitter right in front of the detector. So if the detector has an efficiency eta, we model it as a detector with perfect efficiency, but we put this beam splitter right in front of it, and it has a transmission probability of eta. This is how you model loss in quantum optics. Another really nice thing about modeling loss this way, so I should clarify, I'm talking about linear loss, so loss that applies to single photons kind of equally. So this type of loss also commutes. So if you have two lossy elements in a row, maybe you can model those with, if you wanted to, you could model those with two beam splitters with efficiencies eta 1 and eta 2, or you could just model it as a single beam splitter with an efficiency which is just the product of these two efficiencies. Okay, so let's go back to this entanglement swapping picture that I showed before. But now I'm going to add two beam splitters in, each with transmission efficiency eta. So they're going to represent loss in these transmission modes. And for simplicity, I'm just going to keep these efficiencies equal to each other. It'll make all the equations much simpler, but in principle, these could be different. Okay, so if this is the system that you have, it turns out that it's actually no longer optimal to start with, you still need to start with a qubit and photon entangled state on the left and right sides, but it's not optimal to start with this maximally entangled state or the state that's an equal superposition of excited 0 and ground 1. Instead, it's better to use an unbalanced superposition. And I'll explain why over the next few slides. But for now, I'm just going to parameterize the superposition as some probability 0 of there being no decay photon and some probability 1 of there being a single decay photon in each of these two modes. Again, we can use the same trick where we expand this initial state out into 4 terms, and it looks like this. This is very similar to what we saw before, except now the amplitudes are different. They're these depend on these two probabilities, P0 and P1. And now we can ask the same kind of question that we asked before. So what's the probability if we start with this system with these transmission efficiencies, what's the probability that we detect 2 photons? And the way to answer that is you look at this initial state and we find the term which has the only way to detect 2 photons is if each qubit emits a photon. That's represented by this term of the quantum state here, which has 2 photons in it. And it has an amplitude of the square root of the probability of emitting a photon squared. Or in other words, the probability of detecting 2 photons depends on the probability that each the left and the right qubit emit a photon. So that's P1 squared. And then on top of that, those photons have to be detected. So they have to make it to these detectors without being lost, which we represent by them getting through these beam splitters. So each photon has a probability eta of getting through its beam splitter and then being detected. So we got the overall probability of detecting 2 photons is the probability of emitting a photon and that photon being detected all squared. And I just want to reiterate here that I'm just using a single beam splitter to represent inefficiency for this mode. And so in principle, these detectors could have, they might not be 100% efficient, but that's okay in this model because any inefficiency in the detectors, we can just pull out and just recombine with these 2 beam splitters here. Technically, the way I'm doing this, I'm assuming these 2 detectors have the same efficiency as each other. And again, that's okay for this talk because it just keeps the math a little bit simpler. Okay, so we already saw that the only way to in the ideal case, the way to generate entanglement is to detect one photon in one of these two detectors and no photons in the other. And so we're going to analyze that case here. So again, that's still the situation that's going to lead to entanglement between these two atoms. So just using some simple probabilistic arguments, we can figure out what's the probability of detecting a single photon when you have this loss in the system. And so there's multiple ways, multiple kind of things that can happen, which will lead to a single photon being detected. And I'm just going to go, well, there's 4 of them, and I'm going to go through each of them and build up the 4 terms for this to calculate this probability. So the first way that you could detect one photon is that the qubit on the left emits a photon and it's detected, and the qubit on the right does not emit a photon. And if that happens, so the probability of the qubit on the left emitting a photon is P1. The probability of it then being detected is eta. So you get P1 times eta times P0, the probability of there being no photons from the right side. Similarly, you could have the qubit on the right emit a photon and have it be detected, and the qubit on the left not emit a photon. So you get another term here, which is the same as the first one. And there's 2 more ways that you could detect a single photon with this system. So the first is that, and for each of these 2 ways, what it is that both qubits emit a photon, but one of them gets lost and one of them's detected. So the probability that both qubits emit a photon is P1 squared. The probability that, say, the left one gets detected is eta. So it's not lost with efficiency eta. And then the other photon is lost with efficiency, or with probability 1 minus eta. And similarly, for the 4th term, you could again have both qubits emit a photon, but instead of the one on the left being detected, it's the one on the right that gets detected, and the one on the left is lost. So this is how we can figure out just, what's the probability of getting our success outcome, which is detecting one single photon. But the thing with loss now is that this is going to introduce error terms into the state of these 2 qubits. So for these first 2 terms, what happens is that one photon's emitted and it's detected with, and that's equivalent to the ideal case that we already analyzed. And in that case, that leaves these 2 qubits in this entangled state of ground excited plus excited ground. And depending on which detector it is that clicks, you may or may not have to do a correction with the feed forward. But if you can do that, this is the entangled state that you're left in. And then there's these 2 error terms, and these terms arise from situations where 2 photons are emitted by, one from each qubit, and one's lost and one's detected. And we know in this case that if 2 photons are emitted, then that leaves the atoms in the ground state. So you don't get any entanglement in this case. It leads to an error term. So the overall probability of generating entanglement is given by this expression. That's just the sum of these 2 terms. And the overall probability of getting what looks like a successful outcome from your Bell state measurement, but leaving your qubits in an unentangled state is given by this expression, which again is just the sum of these 2 terms. Okay, so just to clean up the slide a little bit, I'm just removing some of the equations, but these 2 equations I'm going to leave up. And now really the question we want to answer is how much error is there in the final state that we herald. So if we detect a single photon, if we get our successful Bell state measurement outcome, what's the probability that we're left in the entangled state? And similarly, if we detect a photon, what's the probability we're left in an error state? And so we can use Bayes' theorem, or the theorem of conditional probabilities, to answer this question. So Bayes' theorem says that this conditional probability is equal to this ratio. So the probability of A and B happening divided by the probability of B happening. And we can just plug in these 2 expressions to find a simple parameterization of the probability of entanglement given that we got a successful Bell state outcome. And it's this function that depends on the efficiency of the system, the detection efficiency, as well as the probability of emitting a single photon, or the probability, each qubit's individual probability of decaying and emitting a photon. And similarly, for the amount of error, the probability of error given you got a successful Bell state measurement, you can do the same type of calculation and you end up with this state. Okay. So just a quick recap of what we just talked about, entanglement swapping with loss. So the Bell state measurement is going to succeed with this probability. And if the Bell state measurement succeeds, the amount of error in the heralded state is going to be given here. And just staring at this equation for a bit, you can see that the Bell state, this overall success probability of the Bell state, is going to decrease if the efficiency decreases. And the amount of error in the state, it's a little bit harder to see, but it's going to increase if the efficiency increases. Sorry, if the efficiency decreases, the error increases. Okay, now it's time for the next poll question. So let's say that this experiment that I have on the screen here has 100% transmission and detection efficiency. If this is the case, what's the maximum probability that the photonic Bell state measurement will succeed? We'll go 5, 4, 3, 2, 1, and poll. Okay, so this is a good distribution of answers. It seems like most people said either 50% success probability or 100% success probability. Okay, so the answer is actually 50%. And there's two ways to see that. The first might be, you might just remember that when I was going through the ideal Bell state measurement earlier, where I assumed perfect efficiencies, that it succeeded a maximum of 50% of the time. Another way to see that is from this expression for the success probability of the Bell state measurement. So in the question, I said that the efficiency, the transmission and detection efficiency of the experiment was 100%. And what that means is that this eta, this beam splitter, which is representing efficiency, could be equal to 1. So all the light just gets transmitted by each of these beam splitters. So then we can use our expression, the probability of getting a Bell state measurement success is equal to this thing. We can simplify it by replacing eta with 1. And then you find it's just equal to this expression. So, which just depends on this probability P1, which again is P1's the probability that each qubit photon state is in the state where the qubit is in the ground state and the photon has decayed. And okay, finding the maximum of this function, we want to find the maximum success probability as a function of that probability is maybe a little bit hard to do in your head in a Zoom poll, but a nice way to see the answer is you can plot this expression, success probability, as a function of this parameter P1, and it's this inverted parabola, and it has a maximum of 50%, which you get when the probability of decay is also equal to 50%, which corresponds to the maximally entangled state, initial state between the qubit and the photon. Okay. So this is a plot I made. It's a log-log scale, and it's showing what the Bell state measurement success probability is as a function of the detection efficiency of your experiment. So as a function of this parameter eta, again, this parameter eta. What you can see is that the Bell state measurement success probability depends on the amount of error that you're willing to have in the final entangled state between the two qubits. So if you're willing to allow a lot of error, then you can get maybe for reasonable detection efficiencies, you can get reasonable success probabilities. As that detection efficiency decreases down to, say, 1%, your success probability is on the order of, well, I think this is 2%. If you decrease the amount of, if you want to increase the quality of the entanglement that's created, or in other words, decrease the level of error in those final states, it decreases the success probability by a similar factor. So decreasing the error by a factor of 10, in this case, decreases the success probability by a factor of 10. So for any experiment, swapping experiment where there's loss, there's always going to be this trade-off that you can play between the amount of error that you're willing to accept versus the rates that you want to have. Okay. I need to mention that there's a lot of other sources of error in this type of swapping scheme. I'm not going to go into any detail about them today, but I just want to mention that they exist. So for example, you might have imperfect interference visibility if these two decay photons aren't perfectly indistinguishable from each other. The interference in the spell state measurement won't be great, and that will lead to errors in the final entangled state. The detectors could have inefficiencies. Maybe they don't resolve photon number. Maybe they have high levels of background counts. Or maybe just the initial states that you prepare aren't those nice, perfect superpositions that I was drawing, but maybe they had some errors in them as well. All of these things will lead to errors in the final entangled state that's created, and those errors will propagate throughout the quantum network. Okay, so how do we take this single scheme and extend it to larger distances? So now I'm going to talk a little bit about how this type of scheme scales over larger distances. So I talked earlier about how if these qubits have really long excitation lifetimes, then they act as really good quantum memories. So we can generate all pairs. We can, you can attempt to generate each of these individual entangled states separately and just as many times as you want and then you wait until all of them have succeeded at some point. And on average, that's going to take a time that's inversely proportional to the probability of success. So if you have a 10% probability of success of this Bell state measurement, you'll have to try on average 10 times before generating entanglement here. And then if all of these qubit Bell state measurements are really highly efficient, it might be a good strategy to just try them all at the same time. So if each of these has a success probability of P, then the probability of all of them succeeding, and if you try them all at once, is P to the N, if you have N of these intermediate modes. In this picture, it would be P cubed. And so, in principle, the success probability in these matter-based systems can be very close to 1. And if that's the case, that might be the best thing to do. But if you have a lot of nodes or this probability starts to go down, then your overall success probability, P to the N, is going to decrease very quickly because of this exponential scaling. So you could take a different approach, this binary tree approach. And in this case, the first step is similar. You start by generating entanglement individually between each of these pairs of qubits. And then the second step is, so you don't try to implement all qubit Bell state measurements at once, but you do them kind of in neighboring pairs. So in this example, you would do this qubit Bell state measurement to generate entanglement between these two nodes, and you would perform this Bell state measurement to generate entanglement between these two nodes. And the point is that you can do these individually. So if this one happens to fail, you can just try again to generate entanglement on I'll call this half of the network. And the success probability of generating it on half of the network is, or the time it takes to generate entanglement over just half of the network is, again, it's going to be proportional to 1 over the probability of this first stage repeater working times 1 over the probability of the second stage repeater working. And then once both sides of the networks have generated entanglement, then you can try this final Bell state measurement in the middle to generate entanglement between the two ends. And the way that this scheme works is if you have n intermediate nodes and you just keep dividing, you do this binary tree approach, then the total time to generate entanglement is going to be proportional to the inverse of these two probabilities. So the probability of the first stage and then the probability of all the subsequent stages to the power of the log base 2 of the number of nodes in the network. And so if you have a number that's an exponent to the log of a number, that just means that you're this is a function that's polynomial in this number n. Okay, and so because this counts as because it's a polynomial scaling instead of an exponential scaling, this is considered a scalable way to distribute entanglement. Okay, so I really want to emphasize the importance of memories here. So again, I keep making this assumption that the excited state lifetime of these atoms is really long. That assumption's necessary for what I'm talking about because it means that these qubits are really good memories. And remember that every time we do a Bell state measurement, we have to do feed forward to one of the entangled at least one half of the entangled system. And so for the final Bell state measurement that's done in the middle, this final feed forward signal has to go all the way to at least one end of the network. So, and that takes a significant amount of time if you're going over hundreds of kilometers. You know, it could be microseconds or milliseconds, maybe for like country-sized networks, maybe even larger. And so that means that your memories need to have lifetimes that are much longer than that time that it takes the feed forward signal to travel across the network. So a nice feature of this DLCZ scheme is that the initial entanglement's generated between some memory and some photon. And if you can create really good memories, then they can be used to distribute entanglement over these long distances. Okay, and so I know that this is not the first time if you've been in other classes this week, this is not the first time you've seen this specific picture in this specific paper, but this is a really nice example of a quantum networking scheme out of Delft. This paper is from 2021. It's not the most recent paper from this group, but it's a nice example of generating entanglement over a 3-node network. This scheme that they used was the system is a nitrogen defect in a diamond lattice, so in a lattice of carbon atoms that has addressable energy levels. And the nice things about this specific implementation is that the memory lifetimes are on the order of a few milliseconds. But there are some challenges with this scheme. So addressing the energy levels in these atoms is very slow. So the trial rate of the network is very slow, and that leads to an overall very low rate at which they've been able to demonstrate entanglement distribution, only on the order of a few millihertz. And the state fidelities, the fidelities of the states that are made, again, are only on the order of about 70%. So that means these states have 30% error in them. Okay, so now we're getting to the final section of the talk, where I'm going to talk about DLCZ without any matter-based systems and using linear optics and single photon sources. The benefits of these is that they basically have the opposite challenges and advantages of the fully matter-based schemes. So with all linear optics and single photon sources, you can in principle generate entanglement over much, in the megahertz range. So, like 6 orders of magnitude, 5 or 6 orders of magnitude bigger than what's been demonstrated already. And in principle, can have really high state fidelity. So like, above 95, 98%, something like that. The challenge, though, is that it's really difficult to store photons in memories in an efficient way. And so the memory lifetimes of realistic memory lifetimes are much shorter than a few milliseconds. Anyways, okay, so I'll talk about this now. So So Krister talked a little bit about path entanglement in his section. And just to remind everyone, the way that you create a path-entangled state is you take a single photon, send it onto a beam splitter. In this picture, it's a 50-50 beam splitter. And that creates the superposition of the photon being in the left or the right mode. Or I've labeled them here modes 1 and 2, and you get some entanglement here. This is very analogous to the initial state of the qubit and the decay photon that I talked about before. Where here now, instead of one excitation being shared among two photonic paths, it's one excitation shared between an atom and a photon and a photonic mode. But it's, mathematically, these two states are equivalent. So just like you can perform swapping with this matter-based DLCZ scheme, you can just replace the initial qubit photon sources with these path-entangled sources and generate entanglement and perform swapping. And all the swapping math and dependence on loss and all that just works exactly the same as what I already showed, so I'm not going to go over it again. But if you perform this type of swapping, you can end up with path entanglement between these two modes, E and F. And that's the type of entanglement that can be distributed. Okay, so in this picture, I've just drawn single photons coming in, but where did it come from? What source of single photons do we use? So I'm going to talk a little bit about that. And then I'll also mention different options for memories for these types of states. That'll be the rest of the talk. So single photon sources. I already talked a little bit about using atoms or ions that you can control with a control pulse or some artificial atom to force some two-level system to decay and emit a photon. So that can be a good type of single photon source because it can be very on demand. When you send a control pulse, it emits a photon. Typically, these kinds of systems are slow. And a bigger issue is it's really hard to get high collection efficiencies with these photons. Remember, if you want to do secure quantum communication, you need to detect the entangled states with 2/3 efficiency. So that means that this photon in this decay path has to be collected with at least that efficiency and ideally much higher to account for other losses in your system before it's detected. In principle, that's possible. I think the current record for collection efficiency is on the order of 70%, so just above that 2/3 threshold, but not by much. Another type of source, which I'll go into more detail, is a spontaneous parametric downconversion source of photon pairs. These types of sources, they're probabilistic, but they can be heralded, so you know when they've succeeded and when they haven't. They can be really high rates, so trial rates for downconversion sources. This depends on the repetition rate of the pump laser you use to pump it, so that could be hundreds of megahertz. And these photons can be highly, really efficiently coupled into fiber, with greater than roughly 90% efficiency. So what is spontaneous parametric downconversion? I'm going to give a really brief introduction to that. What it is you take a strong pump laser, and it's a process where you send that pump laser into what's called a nonlinear crystal. So it's a crystal where the interaction of the light from the pump laser and the internal polarization of the material polarization of the crystal has some second order nonlinear component to it. And that can lead to an effect where single photons from the pump laser can be split into pairs of photons, which are emitted in the signal 2 modes, which I'll just call the signal mode and the idler mode. So this process has to conserve energy and momentum. That just means that the sum of the two frequencies of any photon pairs created in these 2 modes equals the frequency of the pump laser. And there's a similar formula for momentum conservation. So this is what I've drawn as an extremely simplified picture of a SPDC source. Here's a still very simplified but slightly more complicated picture. In reality, what happens out of an SPDC source is photons don't come out in 2 very nicely defined modes, but they come out in just a range, a spread of spatial modes. which I've tried to represent here by a bunch of different arrows pointing out. But because of momentum conservation, you know that if you detect a photon, say in one of these modes specifically, then it's possible that defines a mode for the other photon. And in principle, if you do all the engineering of your crystal and your pumps and your focusing optics and all of that very carefully, you can, if you detect a photon in one single mode fiber, or if you couple a photon into one single mode fiber, then with very high probability, you will couple its partner in to another single mode fiber, and you won't couple any other light in as well. There's a lot of details that go into this. Calculating these kinds of things is a lot of what we do here. I'm going to skip over all those details though. So the state of a SPDC light, spontaneous parametric down conversion light, that's generated, or maybe that gets coupled into these two fibers, is just written as a superposition of numbers of photon pairs created. So every time you send a laser pulse from your pump laser into this crystal, there's some probability that it generates no pairs, 0 photons in the signal in either mode. Some probability it generates 1 pair, some probability it generates 2 pairs, and et cetera. There's higher order terms. But if you put a heralding detector on one mode, let's say the idler mode, and you count the number of photons that it detects, that tells you something about the number of photons in the signal mode. There's kind of two main types of single photon detectors. The first and maybe most familiar type to many experimentalists is this detector that either clicks or does not click. So what that means is if one or more photons hits the detector, it will click. It'll emit a signal saying, "Hey, I detected something." But it can't tell you any information about the difference between detecting 1 photon or 2 photons, etc. Another type of detector is a number resolving detector. And these types of detectors are nice because they generate a unique outcome for any number of photons that comes in, up to some maximum number. So for example, it could tell you the difference between detecting 1 photon and 2 photons. Okay, so now it's time for the next poll question. So let's say you have an SPD source like I have drawn here, and let's assume that the state of light that gets coupled into each of these 2 single mode fibers is given here. So it's the state I had then on the previous slide, but I just truncated the higher order terms. So if this avalanche photodiode detector in the idler mode has 100% efficiency, and if it clicks, what's the probability that there's exactly 1 photon that got coupled into this fiber? Maybe 5 more seconds for people to answer. 3, 2, 1, and the poll. Okay, so this is sharing. So a lot of people said 100%. And well, these answers are pretty evenly split. The correct answer is actually D. And I was a little bit sneaky with this question on purpose. And one really important piece of information in here was that this avalanche photodiode detector, I had these words on the previous slide. This APD is an example of a detector that clicks or does not click. And so what that means is that if 1 photon hits this detector or 2 photons hit this detector, it's going to click and give the same output signal regardless. So the way that we figure out, so if this clicks, what's the probability that we had 1 photon in the signal mode? Again, we use this conditional probability formula. So it's equal to the probability that there is 1 photon in the signal mode and the detector clicked. So that would be caused by this term here, which is probability P1. Divided just by the probability that this detector will click. And that's given by the sum of these 2 probabilities of there being more than 0 photons in this fiber. So either 1 or 2 photons. So P1 over P1 plus P2. Okay, so the reason that I chose this specific example for this question is just to show that you have to be careful about what type of detector you use when you're heralding an SPDC source. Because if you want to make sure that you have exactly 1 photon in here, it's actually much better to use a number resolving detector. So if we could tell the difference between one photon in the idler mode or two photons in the idler mode, that would really improve the quality of the state that we herald in this detector. And would make us much more likely to herald exactly one photon, which is what we want for a single photon source. Okay, so SPDC is a probabilistic process. So if you send a train of pulses, laser pulses through the signal, you'll get some number of pairs out each time. And I've just drawn some specific pattern of getting 0 and 1 pairs out at a time. I didn't bother to draw double pairs here. And if you have a second source, you'll get a different pattern of times when pairs are generated. And if we want to do swapping between two single photon sources, between two path-entangled single photons, you need those two path-entangled single photons to be generated at the same time. And so because SPDC is probabilistic, if you have some probability P1 of generating a single pair in a pulse, the probability of each source generating a pair at the same time is P1 squared. So that scaling isn't great. So it would be nice if you could go from a probabilistic source to a near deterministic source. One way to do that is you can add a quantum memory in line here and have a feed forward signal from your heralding detector, and it'll say, okay, if this detector detects a single photon, it sends a forward to this quantum memory and it says store the partner photon for some amount of time and then emit it at a specific time later. And that specific time can line up with another photon source. So a simple, okay, so typically when I see the term quantum memory, I think of storing some excitation in some matter-based system. That's not great for this example, again, because with current technology, these matter-based memories are really inefficient. But you could instead use an all-optical memory to do this short-term storage. And the way to explain how that works is just to consider this element called a polarizing beam splitter. So what a polarizing beam splitter does is it's something that you can use to separate and combine different polarizations of light. So for example, if you send a horizontally polarized photon through this PBS, it'll be transmitted straight through. If instead you send a vertically polarized photon through, it will be reflected. And then if you put a pair of mirrors and another polarizing beam splitter in, you can create this type of interferometer where the horizontally polarized light goes straight through, and vertically polarized photons take this longer path, and so they get delayed, with respect to, for example, delta t with respect to the other one. So this is a way to just introduce a time delay. So this is almost a type of quantum memory. You can make this a very simple quantum memory with just two time delays by adding something called a Pockle cell. This is an optical element that if you apply a voltage to it, it will rotate the polarization of light a specific way. So for example, you could just leave it off and it does nothing to the light. So if you send horizontally polarized light in, it goes straight through. But if you turn your Pockle cell on, you can rotate horizontally polarized light to vertically polarized light. It will then take the longer path and get delayed with respect to the other input. So I would consider this a quantum memory, which you can choose one of two times to store the photon for. You can make a more complicated version of this by taking many of these delay interferometers where each delay of each interferometer is twice the delay of the previous one, and use a series of Pockle cells. And then now you can, depending on what voltage is applied to each of these cells, that will determine which path any photon takes through the setup. And you can, for this example, with 3 interferometers, there's 8 total delays that you can choose from. So for example, you could route the photon in this path where it gets a delay of delta t plus 0 plus 4 delta t for a total delay of 5 delta t. This type of system scales pretty well. It scales well. So every time you add a new interferometer, you double the number of delays that you can choose from. The pros are that these types of delays can be really efficient. They can operate really quickly. on these Pockle cells can be switched on nanosecond timescales. The drawbacks are that these types of memories are not suitable for storage times more than something on the order of microseconds or tens of microseconds. So the reason for that is that if you want to delay light by a time of tens of microseconds or longer, you need to introduce a really long delay line. And as we keep talking about, every time you add a long delay to light, it introduces some loss. So as you make the storage time, attempt to make the storage times of these memories longer and longer, the efficiencies will decrease faster and faster. So these are really good, quick, kind of short-term, I would say, memories for single photons. Okay, so our near deterministic single photon source you can create by putting one of these all optical quantum memories or tunable delay lines in. And if you just make sure that the time between laser pulses, if that delta t is equal to the minimum time step of each of these memories, then that can work really well to turn this probabilistic downconvergent source into a near deterministic one. This technology has been demonstrated, really nice work out of the University of Illinois at Urbana-Champaign. Sorry, I'm nearing the end of my time here, so I'm going to go through this very quickly, but this basic idea of delaying a heralded single photon with a Pockle cell inside of a storage loop. This Pockle cell can be used to rotate the polarization to switch the photon out of the storage loop at any desired time. Okay. So if you want to do an all-optical version of path entanglement swapping, this is what it could look like. So you can use these tunable delay line quantum memories, which have a feed-forward signal from your herald detector. And also this herald detector heralds the presence of a single photon of this path from your SPDC source. If you start with two path-entangled states and have the same thing on each side, then this is a way that you can distribute path entanglement between these two spatial modes here. The last couple slides that I have here, I just want to mention matter-based memories. So to the best of my knowledge right now, there's no good way to store a single photon for a really long time in a matter-based system. And the reason is that the efficiency of coupling light to an atom, it's a really difficult engineering challenge, and I don't think high efficiencies have been demonstrated yet. But if you can get your photon into a matter-based memory, then in principle, it can have a really long storage time, much longer than these all-optical memories I was just talking about. And if you're trying to create a large quantum network and you need a really long storage time, then maybe this is a good trade-off to make. Maybe the inefficiency of that memory is okay. And maybe it's worth it to use a matter-based memory. So it's possible that maybe you could consider this hybrid network. So it's some hybrid version between an all-optical path-entangled network and a matter-based network where maybe the first stage of swapping uses these all-optical memories, and then second or higher order stages of swapping use these longer term but less efficient matter-based memories. Okay, so thanks a lot for your attention. And I guess I just want to say that, I think the reason that we're all here in this course is that everyone is, at least to some level, excited about quantum networks and the idea of quantum networking. There's lots of different great ideas for how to do quantum networking. What we talked about today, this idea of distributing path entanglement, it's really only one approach. It has some advantages. Most of the technologies required to implement this that I talked about today have been demonstrated. The high efficiency single photon sources, good heralding, these all-optical memories, etc. Typically, these sources run at really high rates, so megahertz to gigahertz. And there's this possibility of generating these distributed path-entangled states which share this non-local phase information, which could be really useful for quantum sensing. There are challenges, though. This idea of phase stabilization is tricky. It's a tough engineering problem to solve. And then this, for going to very large networks, this idea, better memories need to be developed, I think, before that's going to be feasible. Yeah, okay. Thank you very much for your attention and for listening to Krister and I chat about quantum networks.